So the main result is that matrix transformations are linear transformation. And when I say are, I mean that they are the same thing as. Are the same as. So that's what I mean. So it's a very strong use of the word are here. And so this is very important because that means that you can think of a matrix as a linear transformation. So this is another perspective of what matrices are. There are things you can do arithmetic with, but also matrices are linear transformations. So in order to explain that, let's just first give you the definition. So what is a linear transformation? So definition, a linear transformation also called a linear function, is a function, makes sense, and a function between real vector spaces. It could be like just an ordinary real-valued function from R to R, like what you studied in calculus, but it could be from R2 to R3, it doesn't matter. M and N here are arbitrary, and in order to be linear, it has to satisfy two properties. Linear means that it behaves well with respect to scalar multiplication. So if you scale your input vector, you can just pull out the scaling factor, and it behaves well with respect to addition, and therefore with respect to subtraction. Sometimes there's a slick way to write this just using one equation, but we'll just break it down like this. So these are the properties that a linear transformation, that a function needs to satisfy in order to be a linear transformation. So an example is if M is a matrix, or if A is a matrix, then TA is a linear function. It's a linear function. And why is that true? Let's just go back up. We talked about the properties, where the properties of matrix transformations. So if you look at this property here, property 2 says that you can pull, if you scale a vector by a number, you can pull the scalar out. That's over here. Property 3 says that it distributes well over addition. So in particular, so these are just properties. So these are just properties of TA. So the properties of matrix transformations can be summarized by saying that matrix transformations are examples of linear transformations. Here's a more concrete example, just so we can get a feel for it. Say f from R2 to, say, R, I'll give you a formula for it. F of x, y is going to be the number x plus y. So this is linear. In order for it to be linear, we have to check that it satisfies the two properties. So the first property, so f of, well, if you scale that vector by some number, say k, you scale a vector, you just multiply all the entries in it. So now you have to do the function. The function says you add the first entry and add the second entry. And because we have the distributive property, we can pull out the k. And then this is the same thing as k of f of xy. So it satisfies this property that we can pull out these k's, so that's good. And then f, how does it behave if you take a vector like xy and another vector ab? So, well, first of all, how do we add them? That just means you add the first entries, and then you add the second entries. Okay, now let's do what the function says. The function says add all the entries together. So that's equal to x plus a plus y plus b. Just using the rule, it says add the first entry with the second entry, and we can, of course, rearrange the order of addition. So we can write this as x plus y plus a plus b, and then we can observe that that's the same thing as doing f to the vector xy plus f to the vector ab. So it has this property that f of that vector plus that vector is the same thing as f applied to the first vector plus f applied to the second vector. So that's what this property 2 says. So it satisfies property 1 and property 2. And I'll just give you a non-example. So here's a non-example. Say f, and the dimensions can be arbitrary, but I'm just keeping them simple. So R2 to R2. Oh, I'll use a different symbol. I won't use f. Say g from R2 to R is defined by g, say of xy, spits out the number x times y. So this, it satisfies neither property, actually, so it's nonlinear. So it violates both. This violates both conditions. This violates both conditions. So if you look at the first condition, if you wanted to do g of kx, ky, that would be equal to kx times ky, which is, of course, k squared of xy, which is k squared of f applied to xy. And that is, of course, not k of f of xy. So this is what we want. Sorry, I started writing g, and then I started with an f, then I changed it to a g, and then I went back to, sorry, so this function is called g. Sorry. So we want that, if you scale it, it has to plot, but we just saw that it's not equal, so it violates the first condition. And if it violates one of the conditions, then it can't be linear. It has to satisfy both. So at this point, we can conclude that it is nonlinear. But it also, just to illustrate, it also violates condition 2, because if you wanted to add these things, well, that's the same as doing g of x plus a, y plus b, and by definition, that would be x plus a times y plus b. But because we have the distributive property, we end up getting xy, and we end up getting ab, but we also have xb and ay. And so this first thing would be g applied to xy, and the second thing would be g applied to ab, but then we still have this extra stuff. So this is certainly not equal to g of xy plus g of ab because of this extra stuff. So this is extra stuff. So, and thus that stuff happens to be 0, so